Okay, so in part two, we're going to be talking about partial neutralization. So partial neutralization sounds like, it means exactly what it sounds like. It's when a neutralization reaction isn't complete and only happens part of the way, which means we don't have a pH of exactly 7, and the concentration of hydrogen ions, I'm just going to put that here. The concentration of hydrogen ions does not equal the concentration of hydroxide ions in a partial neutralization. So, there was an example like this in the Activity 7 lesson, and we're going to go through this and break it down. So, a titration of 50 milliliters of potassium hydroxide, 0.1 molar, is done with hydrobromic acid with also a molarity of 0.1 molar. Calculate the initial and final pH of the solution after 35 milliliters of hydrobromic acid has been added. So the first thing I like to do when I see a problem like this is I like to underline all the information that I'm given. So I'm given 2 molarities and 2 volumes. I'm told what my base and my acid are. And then in terms of what I'm asked for, we're asked for initial and final pH. So the first part of this word problem is just finding the initial pH. Now, it can be a little bit tricky to figure out what that is, but all it really takes is for you to carefully read the problem and comprehend what it's telling you. And then you just need to use some logic to figure out what was first and what's being added to what. So the initial and final pH. If we read the question again and we see a titration of 50 milliliters of potassium hydroxide is done with hydrobromic acid, calculate the initial and final pH of the solution after 35 milliliters of hydrobromic acid has been added. So it's telling us right there, initial and final pH of the solution after the acid was added. Because it's telling me it wants to know before and after the acid, that means there was a before the acid, which means logically the initial solution only had base. Right? That's how that works. We just reasoned our way through that. We know that the initial solution only had base, which means that if we want to find the initial pH, it's going to be of the base. So we know that we have potassium hydroxide, 0.1 molar, and because potassium hydroxide only would dissociate to release one hydroxide ion per potassium hydroxide compound, it's a 1-to-1 ratio, right? And let me just make that quick. So we know that because it's 1-to-1, any sort of the molarity or the number of moles of potassium hydroxide will be the same as the moles of OH. So we can find the POH because we have the concentration of hydroxide. This is something that I noticed a few of us making errors on in this unit. Okay, if you're starting with hydroxide, you cannot find the pH with that information. You have to find the POH, because if you only have base, bases do not dissociate to produce hydrogen ions. They produce hydroxide ions. So you need the POH. And we already know that it's 0.1 molar. That's the concentration. So it's the negative log of 0.1 molar. And when you type this in your calculator, you'll end up getting a POH equal to 1, which that's very, very basic. And then once we get that POH, remember that pH plus POH equals 14. So if we want the pH, then that's 14 minus the POH, just did some quick algebra there, and 14 minus 1 is 13. So therefore, the initial pH of that solution, of that base, is 13. Now, we want to move on to trying to calculate the final pH of the solution. To be able to find the final pH of the solution, we need to find out how many of these hydroxide ions were neutralized, how many of them reacted or combined with hydrogen ions to neutralize and form water. So our second step here is we need to then look to see the molar ratio of hydrogen ions and hydroxide ions to their component parent acid and base. So we know that hydrobromic acid dissociates to give you one hydrogen ion and a bromine anion. And potassium hydroxide dissociates to give you a potassium cation and a hydroxide anion. And in both cases, we see these are balanced ionic equations. It's a 1-to-1. So 1-to-1 ratio there. Which means that once we calculate the moles of the acid and the base, then since it's a 1-to-1 ratio, we've automatically calculated the moles of, or the quantity of hydrogen ions and hydroxide ions. So if we want the moles of hydrobromic acid, which equals the moles of hydrogen ions, because we know it's a 1-to-1 ratio, then we can solve that by taking the concentration or the molarity, right? So I'm just going to say C for concentration, and then we multiply that by the volume. So if we have 0.1 molar, which we did to just make things simple, and then pay attention to volume, okay? We want 35 milliliters, but because we're dealing with molars, which is moles per liter, we have to write it in liters. So 35 milliliters in liters is 0.035 liters. I'm not going to go over how to convert that. Okay, and then once we solve that, we get 0.035 moles of hydrogen ions. And then if we want the moles of the hydroxide ions, which again we know because it's a 1-to-1 ratio, it's the same thing, concentration or the molarity times volume, which is also 0.1 molar, times 0.05 liters, because we had 50 milliliters there. And in that example, we get 0.05 moles of hydroxide ions. Now, I have the moles of hydrogen ions and the moles of hydroxide ions. And right now, all I'm going to do is I'm looking at these to see which one has more, because that's going to tell us what ends up being in excess at the end of the partial neutralization. When I compare these, I see that there are more moles of hydroxide ion than hydrogen ion. Right? So I can see there's a surplus or excess of hydroxide. And then to figure out what that excess is, we simply just need to find the difference between the two numbers. So 0.05 moles minus 0.0035 moles is 0.015 moles of hydroxide ion that's left over. And I can do this, right? I can simply find the difference between the two numbers, because no matter what, hydrogen ion and hydroxide ion always react with each other in a 1-to-1 ratio. It takes one hydrogen ion and one hydroxide ion to form a water. So that's why I know that 0.0035 moles of H plus can neutralize 0.0035 moles of hydroxide. That's why we could do this step and why conceptually it works. So now we know what the moles of hydroxide are, but now we need to find the total volume of the solution. Again, this is more just logic and reasoning, because we know the final solution has a larger volume than the initial one, because we took 50 mils and then we added 35 mils to that. Which means that the total volume of the final solution is going to be 85 milliliters, or 0.085 liters. And now we want to start looking for the final pH, because we now have moles and we have volume, which means we can start finding concentration, which is what pH is. So again, because we have excess hydroxide, we need to find the pOH first. So in this, the concentration of the hydroxide ions is going to be, right, C equals N over V, or moles divided by volume. And then when you plug this in on your calculator, you will get 0.01765 approximately moles per liter. So that's our concentration of hydroxide. Then we want to find the pOH, which is the negative log of the concentration of hydroxide ions, which we found. And then when you find the pOH, you're going to get a value of around 1.75. But we were asked for the pH, which, remember, pH plus pOH equals 14. And as we saw up here, pH equals 14 minus pOH, or 14 minus 1.75, which should give you about 12.25. So that would be the final pH of the solution. Right, and we can know that this makes sense because we started with an initial pH of 13, which was very basic. And then after we added some acid there, the pH of the solution came down to 12.25, which means that the pH of the solution actually decreased and became more acidic, which is exactly conceptually what you would expect to happen once you added an acid to a basic solution. So I'm going to leave this video for that example. I'll have one more to show you guys in this playlist.